Unlock the potential of artificial intelligence. Welcome to Deep Learning and Generative AI.
This is part 1 of our lecture on recurrent neural networks. In this session, we introduce sequence modeling, derive the RNN formulation, and examine the challenges of training recurrent networks. All right, let's lay out our plan for this session. We're going to start with the why we even need special models for sequences in the first place. Then we'll build up a solid probabilistic foundation, and from there, the vanilla RNN architecture will emerge quite naturally. After we see how it works, we'll dive into how to train it, and maybe more importantly, why training can be so tricky. We'll wrap things up by looking at a classic application, language modeling. So let's start with a fundamental question. Why can't we just throw a standard feedforward network, or a CNN, at problems involving text or audio or time series data? Well, it all comes down to a single, critical assumption that these models make. See, most of the models you're probably familiar with assume that the data is independent and identically distributed, or IID for short. Think about the image on the left, a bunch of book purchases. Does it matter what order we look at them in? Not really. The dataset means the same thing. But now look at the right. That's an audio waveform. Order is everything. The information, the meaning, it's all baked into the sequence, into the temporal structure. If you were to shuffle the time steps of that audio clip, you just get noise. It would be completely meaningless. And that's the core challenge we're here to solve. Okay, so to tackle this properly, we need to move beyond just intuition and frame the problem in a more rigorous way. Let's define our goal using the language of probability. What we really want to do is model the joint probability of an entire sequence. The probability of observing x1, then x2, all the way up to xt. And it turns out there's a beautiful way to break this down using the chain rule of probability. We can factor this massive joint probability into a product of conditional probabilities. And look at what each term represents. It's the probability of the current token given all the tokens that came before it. This is exactly what we want. This approach is called autoregressive modeling, and it's a really elegant way to capture this idea of sequential dependency. Now there's a catch. If your sequence gets long, that conditioning context, the entire past, gets huge and becomes totally unmanageable. A simple fix might be a Markov model, where you say, okay, forget the entire past, I'll just look at the last, say, 5 tokens. But that's a pretty severe limitation, right? It means you can't capture any long-range dependencies. A much smarter idea is the one on the right, the latent autoregressive model. The idea here is to maintain a summary of the entire history, a latent state we'll call H. This state is a compact, fixed-size representation that, hopefully, compresses all the important information from the past that we need to make our next prediction. So that leads us to the big architectural question. How do we actually compute this summary state, H, and how do we update it as we move through the sequence? The answer to that is the Recurrent Neural Network, or RNN. Let's break down the mechanics. It's actually quite simple at its core. At any time step t, the new hidden state, ht, is just a function of 2 things, the state from the previous time step, ht-1, and the current input, xt. As you can see in the equation, we take the old state and the new input, multiply them by some weight matrices, add a bias, and then squash it all through a nonlinearity like a tan. That's it. That's our new state. And the real magic is that those weight matrices, WHH and WXH, are the exact same at every single time step. We're reusing them. That's how the network learns a consistent rule for updating its memory. Now, that little recurrent loop in the diagram can be a bit hard to reason about. So here's a really powerful way to think about it. We can unroll the network through time. Look at this diagram. The compact, loopy version on the left is exactly equivalent to the long, unrolled chain on the right. And when you look at it that way, a light bulb should go off. An RNN is really just a very, very deep feed-forward network. The depth isn't a hyperparameter you choose. The depth is the length of your sequence. And here's the kicker. Every single layer in this deep network shares the exact same weights. This is the crucial insight you need to understand how we train them. Okay, so if an RNN is just a deep network with shared weights, that gives us a huge clue about how to train it. We can use our old friend backpropagation with a slight twist. The process is called backpropagation through time, or BPTT, and it works exactly like you'd expect. First, you take your network and you unroll it for the entire sequence, just like we saw. Second, you do a forward pass, feeding your data through step-by-step to get all your outputs and calculate your total loss. Third, you start the backward pass, propagating the error gradient all the way from the end of the sequence back to the very beginning. And fourth, this is the important part. Since the weights are shared,
The gradient for a weight at, say, time step 5 and the gradient for that same weight at time step 50 both need to be added together before you update the parameter. You accumulate the gradients across all time steps.
This picture shows that flow perfectly. You've got the red arrows showing the gradients flowing backward from each time step's loss. And you can see how the gradient for that recurrent weight matrix, WHH, isn't just from one place. It's the sum of all these signals flowing back from the future. Every single future step has something to say about how that shared weight should be updated. And right there, in that elegant design, lies the Achilles heel of the vanilla RNN. This very deep weight-sharing structure is a recipe for numerical instability during training. Let's just glance at the math for a second. To get the gradient of a loss with respect to some hidden state way back in the past, the chain rule tells us we have to multiply a whole bunch of Jacobian matrices together. And because of the weight sharing, every single one of those Jacobians involves the same recurrent weight matrix, WAH. So to backpropagate a signal over, say, 100 time steps, you are literally multiplying the same matrix by itself 100 times. This is the mathematical root cause of all our problems. So what happens when you multiply a matrix by itself over and over? Well, its values tend to go to one of two extremes. They either explode towards infinity or they vanish towards 0. It all depends on the eigenvalues of that matrix. If the largest one is greater than 1, your gradients will grow exponentially as they travel back in time. We call this exploding gradients. Your model updates will be huge and chaotic. If the largest eigenvalue is less than 1, the gradients will shrink exponentially. We call this vanishing gradients. The signal from the distant past effectively becomes 0, meaning the model simply cannot learn long-range dependencies. It's like it has short-term memory loss. Now, over the years, we've developed some practical workarounds. For exploding gradients, the solution is a bit of a hack, but it works surprisingly well. Gradient clipping. If your gradient vector gets too big, you just shrink it down. You cap its magnitude. For the vanishing gradient problem and the sheer cost of backpropagating through thousands of steps, we often use truncated BPTT. Here, we just decide to only backpropagate for, say, the last 100 steps, and we cut off the gradient flow from anything before that. It's not a perfect solution, but it makes training tractable. Okay, enough theory. Let's ground all of this in a real-world task. The classic example for an RNN is language modeling. So let's say we want to build a model that predicts the next character in a sequence. Here's how it works. We take a character, like M, and we turn it into a dense vector using an embedding layer. We feed that vector into our RNN. The RNN updates its hidden state, trying to remember, okay, I've just seen an M. Then the next character, A, comes in. The RNN takes its memory of M and combines it with the new A to update its state again. This continues for C and H. Finally, after seeing match, we take that final hidden state, pass it through a linear layer and a softmax, and it spits out a probability distribution over all possible next characters. And hopefully, it gives a really high probability to the character I. That all seems to make sense. But how do we actually measure how good our model is? How do we put a number on its performance? The go-to metric here is called perplexity. The mathematical formula can look a little intimidating, but the intuition is fantastic. You can think of perplexity as the weighted branching factor. Basically, it's a measure of how many choices the model is, on average, confused about for the next token. So a lower perplexity is better. A perplexity of 10 means that at each step, the model is about as uncertain as if it were choosing between 10 different options. A perfect model would have a perplexity of 1, because it would be absolutely certain of the correct next word. So let's just step back and summarize the core issues with this vanilla RNN we've built. First, vanishing gradients give it a serious recency bias. It struggles to connect what's happening now with something that happened a long time ago in the sequence. Second, that fixed size hidden state has to be a summary of everything. It has no explicit mechanism to say, this piece of information is really important, I should hold on to it, or this other bit is just noise, I should forget it. This creates a massive information bottleneck. In the next part, we examine how gated architectures such as LSTMs and GRUs address the limitations of vanilla recurrent networks.